Okay, so let's continue. We are aware that so far we are in the class material is week 4 class material. Wait a second. I have to pick myself. Okay, I had a problem with the camera, so things looks better. Anyway, it takes a few seconds, few minutes to set up everything. So if you remember, the last time we were talking about the pointing vector. The pointing vector, it's a quantity which we denoted as s, which is a function of z and t. Okay, and this was equal to e, which is a function of z and t, cross h as a function of z and t. So, but this quantity, this does not make much sense. This is not the best word to say. This doesn't make much sense. It's not the perfect word to mention. But what is more essential for us is the time average of this quantity. Okay, so that's more important because we are talking about instantaneous expression. We know that when this is expressed as an instantaneous expression, we are talking how it is changing every nanosecond. Okay, we're talking about a nanosecond because the frequencies which we often communicate with, or that we most often use, are the type of gigahertz. Okay, 5 gigahertz or 800 megahertz at the least. Okay, the first cell phones that were around, they were running around 800 megahertz to 900 megahertz. So that's what we are talking. So we don't care much about this one. What we care most is this quantity, which is time average. So we can call this one the time average. This is equal to the integral from 0 to a full period of sz(t) dt. Okay, so this is much more essential, and this is a quantity which has a unit of watt per meter square. So it is power per meter square. So for example, you have let's say there is an antenna. So this antenna is emitting a wave, okay, or a signal, which is often, mostly done by having an alternating current source with a specific design, like antennas do it, and they emit an electric field and a magnetic field. We can calculate the power density per unit area at a specific distance. Okay, so that's what. Wait a second. Yes. So this would be watt per meter square. Okay. So this is what we can emit. But then the total power of an antenna, which you can calculate, is this quantity. So it's going to be the cross product of E and T, and then we have to integrate over the outer surface area. So let's think for a moment that here we have an antenna which is emitting some signal. So this has an associated electric field, associated magnetic field intensity. Then you come to a very far away distance. Calculating the average pointing vector, we find how much power we generate over 1 meter with another 1 meter. So we find power per meter square. But then if we multiply this average pointing vector with 4 pi r squared with the surface area of this hole, which are equidistant to the source, you can find the total power which is emitted by an antenna or by a device, or even including, let's say, the sun itself. It's a source which is emitting a lot of photons, and these photons have representative electric fields and magnetic fields. So we can calculate the total power, and you know what the total power would be then. So if this time average pointing vector has a unit of watt per meter square, okay, we multiply this one with 4 pi r squared, which has unit of meter square. So we cancel out these, and we really get the total power which is emitted by a system. So this is what we covered the last time, and I could repeat again that going over the good examples in the textbook, they would help you a lot. So from this Okay. So let's pick up this example. Let's assume that we have an antenna. It emits at 1 gigahertz, okay? So it emits at 1 gigahertz, and it has a total power. It radiates total power around 1 megawatt. Okay, so this is the total power of this antenna. And now at so let's say at a distance which is expressed as 380 times 10 to the power 6 meters. Okay, so this is a very long faraway distance. Let's find the time average power density. Find so when we talk about the time average power density, what do we understand? In this case, we would understand this quantity here, okay, time average power density. Because the power density, it is like it's the pointing vector itself. So in this case, we can write that. Actually, this is we denote this one sometimes by S or by P, but it's since this is a power density, let's write it like this. But pointing vector is often also denoted by an S. So this would be equal to total power, okay, divided by 4 pi r squared. So if this is the total power, we divide by the total area, and we find what is going to be per unit meter squared. So here we get 10 to the power 6 watt divided by 4 pi times 380 squared times 10 to the power 6 all squared. This would be equal to, so we can somehow, we can notice that this 10 to the power 6 divided by 1 to 10 to the power 6 here, we are left with, let's see what we get approximately. So we might get 1 over 10 to the power 6 is this one. Then 380, this could be something like 10 to the power 3 squared, 10 to the power 6, like another 10 to the power 6. So just checking the order of the numbers, it looks like we're going to get a number which is in the order of 10 to the power minus 12, if we are not mistaken. And if you substitute all the numbers, we get something like 5.5 times 10 to the power minus 13 watt per meter squared. So this is the time average power density, and this is the unit that we were expecting from this specific quantity, which we explained it here. So if this is this quantity, the next question is, what is the amplitude of this field? What is the amplitude of E? And now the amplitude of E, we know that this quantity, we could even write this one here, this would be equal, so if we take away the unit for a moment, this is equal to the amplitude squared, okay, divided by 2 times intrinsic impedance. So this time, when we are asked about to find the amplitude of E, this number here would be equal to E squared over 2 intrinsic impedance. So we have to multiply this number by 2 eta and this intrinsic impedance, if we are talking about vacuum, if we have no material, this is 377 ohm, because this is for vacuum or air, and in this case we'll get something like 10 to the power 377 times 2 is like 1,000. 1,000 times 10 to the power minus 13, we get 10 to the power minus 10. Square root of 10 to the power minus 10 is something around 10 to the power minus 5. Okay? So just if you consider the order, we are talking about something 10 to the power minus 5. What is this? This is 10 to the power minus 5 volt per meter. Okay, so this is the strength approximate. We did not write the numbers, but we should always be aware of how to get an approximate order of the magnitude. And this would be something like 10 to the power minus 2 millivolt per meter. Okay? Or this would be equal to, what is this? Times 10 to the power 3, this would be 10 microvolt per meter. Okay, so we could even measure a microvolt, which would be 10 to the power minus 6. So if we substitute these numbers here, we find that the electric field, it should be equal to 5.5 times 10 to the power minus 13 times 2 times 377. This is all square root. So with this amplitude, we are going to get something like 2 times 10 to the power minus 5 volt per meter. Okay, so this is one example about the time average power density of the Poynting vector. Okay. And in fact, if we have antennas that radiate at a specific frequency, there are some standards which should be obeyed, that we have to obey, in order to protect the safety of individuals. And I think I have it written here, and the safety limit for the power density is 2 watt per meter square. So the safety limit, is 2 watt per meter square. Okay, so if you keep this in mind, you can always try to, once you are given, let's say, anything that radiates. Okay, it could be a laser pointer. Okay, you have a laser, and you point to some. Of course, often they are restricted to a very small area, so they might be restricted something like 2 millimeter by 2 millimeter. Okay, at a specific distance. So if we divide it, probably they are well beyond the safety limit, because you are dividing a very high power in a very small surface area. It's not that you are spreading it out, but with this limit. So here apparently this antenna, this radiates. It has a time average power density, something like 10 to the power minus 13 watt per meter square. So it is very safe, being that it's a very high. So we are actually very far. Okay, so the distance is like 380. Is at least 10 to the power 2 meters. 10 to the power 2 times 10 to the power 6, we get 10 to the power 8. This is very large distance. So it is safe. Probably if you get much more closer to this antenna, it's gonna be beyond the safety limits. But we have to be also careful about these numbers, or at least it's good to be aware that these are some parameters that we need to be careful about. Now, with this new material, because once we have these safety limits, we can define some relevant quantities. And these relevant quantities, it's good to talk about the radiation pressure. Because we see that if we see these quantities, we have apparently we just have an electromagnetic wave. Okay, it's an oscillation of which is denoted or is represented by an electric field which oscillates, and apparently this applies some watt. But this watt, these are energy per unit time. Okay, so if this quantity which is here watt per meter square, let's take a note here, this quantity. This watt per meter square, we know that this is joule per second, okay? Joule per unit time is watt times 1/meter square. So once we see these joules, it looks like there is some energy that we generate, and we can even try to determine some relevant quantities by remembering, for example, that pressure. Let me write this one because P, we see this P power a lot, but let's assume that pressure, which is measured in Newton per meter square, we can we can try to find a relationship between this pressure, which is measured in these units, with these, because we know it looks like we can find this pressure somewhere in this quantity, okay, because it's a joule per meter square. What is the relationship of joule with Newton? We know that the energy or work, which is measured in joule, this is equal to force times distance. So joule J would be equal to Newton times meters. And from these, if you play around with the units, you can even derive the relationship for the pressure. So now the radiation pressure, this says units, at least let's write first the units. So this is going to be Newton per meter square. And we can also define momentum. We can have a quantity, which we are going to call this one delta G. This, we can write this one as time average power density times delta area times delta T, okay, divided by the speed of light, okay. So if we look at this quantity, this delta G, this is denoted as the momentum delivered. This is momentum delivered at an area delta A, okay? So this delta A is measured in meter square. So again, if you look at these units, you know that this is watt per meter square, times meter square is just watt, times seconds, watt times second is equal to joule. So joule divided by meter per second, we get the momentum delivered. So just to remember, what is momentum in classical physics? What is the unit of momentum? Unit of momentum is P, which is equal to mass times velocity. So what we can do, so this is equal to kilogram times meter per second. Then, if we multiply this momentum by another velocity, so if we have here mv, let's multiply with another v, velocity, which in the case of waves, we can denote this one also like mc times c, where c is the speed of light. Okay, this is how far the waves are moving. So what is the unit now? This is, we also remember, this is an equivalent sign, not equal. We know that 1/2 mv squared, what is this? This is like the kinetic energy, which is measured in joule. So it looks like if we multiply this quantity by the speed, we get here on this side joule. So this is the momentum derived. So let's see, momentum, it was momentum delivered at a surface area delta A. This is how we define this one. And let's check again. So it looks like this time average power density. So let's write just the units here. So we have this expression. We're trying to draw some conclusions here, but let's check again. This is joule per second times meter squared is just the S. It's this quantity. This is the unit times meter squared times second. Okay, so they cancel out. Second cancels out because there are these two divided by the speed of light. Speed of light has unit of meter per second. Okay. So it looks like joule divided by meter per second, what is it? So this is also joule, just using the principles of whatever we can remember from classical mechanics. Okay? So joule divided by meter per second, which is one of these, we get momentum. Okay, so it looks like we are good. So here we define the momentum delivered at the delta A, and also we look carefully at the units. And this quantity we can derive a time average force. Time average force is equal to the time average power density times delta area divided by c, by the speed of light. And how do we get this? We get this because we know that the force is equal to delta p over delta t, okay? Or we often write this one dp over dt, because force is equal to mass times acceleration, and this is equal to mass times velocity divided by time, or this is going to be mass times dv over dt. So far, it looks like, at least for the sake of respecting the units, we can draw, or we can derive a relationship between the specific quantities in the wave, electromagnetic waves, with the same quantities which are equivalent in the classical mechanics. So this is the time average force, and if this is the time average force, we can define also time average pressure. Let me write this pressure because we have powers everywhere, it might be confusing, but this is pressure. Time average pressure, this is equal to the time average power density divided by C. So now we have a unit which is Newton per meter square. This is Newton. Okay, so this is some relevant quantities, and these we can take this away because we're just trying to remind each other about relevant relationships. So let's provide here another example. So if we have radiation with time average power density, which would be around 1400 watt per meter square. Okay, so this is time average power density, and then let's try to, and this is actually the sun radiation. So the sun, the star of our solar system. Let's try this one, sun radiation. And this would be, we can find actually what is the pressure by the sun here on planet Earth. So pressure, if we look at these expressions, so let's say what is the pressure? This is the question. We can look at this expression, apparently is the time average power density divided by C. This is all which is going to have. So here we have 1400 watt divided by 3 times 10 to the power 8, because this is the speed of light, which we have this expression here. And finally, we have here 10 to the power 3 divided by 10 to the power 8. We should get a number approximately 10 to the power minus 5. And the unit would be meter per Newton per meter square. So it's a number approximately 10 to the power minus 5 Newton per meter square. What does this correspond to? Let's remember that we know that 1 kilogram is approximately, not approximately, it's equal actually, but or approximately 10 Newton. So if this is 10 to the power minus 5 Newton per meter square, we can divide by another 10, and this is equivalent, like 10 to the power minus 6 kilogram per meter square, okay? So it looks like in a sunny day, if we are at the seaside, because the sun is there, we can assume that we have a surface area. You can open a piece of metal, and it looks like on a surface area of 1 meter square, you have what is a kilogram, milligram, and microgram. So no, what is it? We have something like, how do you count this? A gram, this is 10 to the power minus 3 gram per meter square, and 10 to the power minus 3 gram, this is milligram. Yes, we have 1 milligram per meter square. So this is how much weight. It's like a small piece of sand. It will drop on a 1 meter square. That's how much weight this is going to add. Okay. Probably it's not that much. And let's see actually pressure. So if this is the pressure by the sun, we can also try to define other relevant quantities. But probably this is enough just to pick up the relevant order of magnitudes or the relevant quantities. Let's see another example. But we can also assume, consider the following. We did not write the number, I think. Oh, okay, sorry. The pressure we said is going to be something like this, but pressure of the sun. Newton per meter square. Okay, so this is what we are going to get. So this was just checking the order of magnitude of the effect that we can have. Let's assume for a moment if we have a laser, another example. So this is a second example. We can have a laser which has a power around 3 milliwatt. Okay. This could be a 3 milliwatt, and this has a spot of 2 millimeter in diameter. So we said that if we have a laser pointer that we use sometimes in the classrooms to point somewhere, those laser pointers, they make a relatively small point. This is 3 milliwatt per millimeter square. And let's try to identify what is the time average power density. So let's try to identify this. And whenever we try to identify this one from the given quantities, we should not forget that this has a unit of, so this is the question, find this. And the unit of this is watt per meter square, okay? And then just by looking at the unit, probably you don't, sometimes you may not even need to look at the formula sheet or at the cheat sheet, but just by looking at the units, you may extract the relevant relationship. So let's assume also that, okay, so we divide this one by the areas pi r squared. So here we go. So we can divide this one. Let's add this one power divided by area. And this is equal to 3 times 10 to the power minus 3. This is what? Divided by the area, which is equal to pi r squared. Okay? Area is pi r squared. And this would be pi times, if the spot is 2 millimeter, that means the radius is 1. So the radius would be half. So this is going to be 1 squared. 1 millimeter is 10 to the power minus 3 squared. So we get pi times 10 to the power minus 6. Pi times 10 to the power minus 6. So we write this down, pi divided by 10 to the power minus 6, and it looks like roughly we're going to get a time average power density of something 10 to the power plus 3. Okay, 10 to the power plus 3 watt per meter squared. Now, if you remember, what was the safety limit? I've not written the numbers, but in order for you to follow, for us to follow each other, it was something like it was 2 watt per meter squared. That's how I remember the safety limit. Now, here we get something like 10 to the power 3 watt per meter square, which means that this is beyond the safety limits. So it's a small power, 3 milliwatt, but it's concentrated in 1 millimeter square or with a diameter of 2 millimeter, which means the surface area of pi r squared. And finally, we get the exact value. This is going to be equal to 955 watt per meter squared. Is everything all right so far? Can somebody confirm using the microphone?
Yes.
Okay, thanks. Thanks. And no, you could help me. Thanks, Bjorna, for the comment. And you'd greatly help me when I enter the attendance if you are kindly write in the comment section or in the chat session present, or you just press 1. Okay, so I want to see it. This would be a help to me. Okay, so this was an example for the laser pointer, and what else we can do? Let's assume, for example, what is going to be. Yes?
I don't know if you will need it, but there is a Google extension which can take the present in Google Meets.
Yes, but it didn't pop up. Normally, it pops up like an advertising thing, which I say okay, but I did not get it this morning. Did you feel it?
Okay.
You are right.
No.
Unfortunately, every time when I come to class, it does come up. That one is really good because it also shows how many minutes, hours you have stayed online. I mean, the same session. But for some reason, I don't even see it here. So there is this in the Google Classroom window, which I see in my screen here. I don't see that good-looking with extra feature spot. Okay. So okay, thank you for reminding me this, but this was the case. Now, let's assume that you have this laser power, which you hit it. Imagine for a moment, you have this laser pointer, you press it, it hits the board, and it reflects back. Okay. But let's assume that this reflection, it has a coefficient of 70%. It could, and we may want to find what is the pressure. So what is the pressure at a reflection 0.7? Okay, reflection at a 0.7. This would be equal to 1 plus 0.7 times S divided by. So we use the same expression IC. Okay. So in this case, this would be 1.7. Why do we say it like this? Because there's always, when you hit with something, you get that much pressure. If the material is absorbing everything, the pressure would be just this value. But if the material is 100% reflective, let's say that 100% of the light is going to reflect back, then this would be 1 plus 1. It would be twice. Okay. But in this case, we get 1.7 times 955 divided by 3 times 10 to the power 8. Okay, so in this case, we get a pressure which is of the order 5.4 times 10 to the power minus 6. So it looks like this is 10 to the power minus 6, and the unit is Newton per meter square. Newton per meter square. So it looks like this is 1 order less. Then this is 1 order less than the power which comes from the pressure that is coming from the sun. Okay, that's interesting. So I never checked about that one, but this is what we get. Is everything clear? Okay, if you like, we can have a short break, 5 to 10 minutes break, and we'll continue again.